to complete our little tour of GR. Of course, I mean, as I said, I mean, it's not possible to really go through the details of either the calculations nor the ideas involved. So it was just a sketch. So let's just conclude the sketch with today's lecture with a recap of what we did in the last class. So we started with the description of space-time by a metric connection. So we say that our universe is essentially a four-dimensional manifold with a metric structure, which is non-trivial, of course, and we could have possibly have lived in a universe where there were no metric, but it so happens that we do have, and it's a smooth manifold, so the space-time doesn't have strange discontinuities and non-trivial structures when it comes to differentiability and continuity and things like that. So everything is smooth. The fields that we are interested in are also smooth. And in such a manifold, we have the metric G mu nu, which has the complete geometric information. Right? So that encapsulates the entire geometric picture. And then we said that the cause of this space-time to have a certain metric, which is different from, say, the flat Euclidean or the Minkowski metric, is essentially because space-time is not vacuum and there is matter. And the presence of matter changes the geometry of space-time so as to, in a way, such that we have a general G mu nu instead of the eta. And we made this important statement that from eta mu nu to G mu nu, this transformation can, in principle, be just a coordinate artifact. We could start with just the flat space-time and do some coordinate transformation and make the space-time look weird and curvilinear. But clearly that has got nothing to do with the intrinsic curvilinearity of the space-time. So there has to be something which is going to say that yes, it is flat or it is not flat. I mean, there has to be some quantifier. Of course, we also said that the converse, there is a problem here because if you have a curvilinear coordinate system or a non-trivial G mu nu, whatever, you can possibly, by some coordinate transformation, reduce it to the Euclidean form. If you can do that, globally, then of course you say that, well, the fact that G mu nu was not flat, did not look like the flat, it was purely a coordinate thing. But it is not guaranteed, and of course in an arbitrary general manifold, you can only do this locally. You can only locally make a coordinate transformation at a given point and make this G. So this is a function of coordinates. Right? So you can always make this function at a given point look like the diagonal 1 minus 1 minus 1 of the eta, but you cannot do it globally. So that is very important. So the local structure is Minkowski, but these little patches of Euclidean space is sort of sewn into each other in a very nice, smooth manner, but the global structure cannot be described by the Euclidean metric. This is what we discussed last time. And so we also went into the discussion of how this changes what it basically does to the geometry. So we saw that, of course, other than changing the rules of calculating distances, one has to also change the rules for differentiation, because one has to introduce the idea of a parallel transport of a vector, which will now include geometric pieces arising from the derivatives of G. And then we also saw certain interesting results relating to that. The next thing which we discussed last time, so we'll go back one slide and have a look. So we started with this idea of trying to quantify curvature of space-time, and we saw that if we take a vector and we make a parallel transport around a closed loop, then essentially if there is curvature at the point inside in the region that this loop sort of encircles, then clearly this quantity, this delta mu, won't be 0 because there will be a net change of the vector by virtue of this, and it's going to be proportional to this fourth rank tensor. So that is what we saw, and clearly by using, this looks pretty complicated, but it's basically just by using the Stokes theorem, you can just write down the form of the Riemann tensor. And you can clearly see it contains derivatives of gamma. And we also said that you can make the gammas go to 0 locally by choosing a certain coordinate system, locally making this G mu nu look like this. You can make the gammas vanish at a point, but you can still not make the derivatives of gammas vanish at the point. So thereby you cannot, by any coordinate system or coordinate transformation, reduce the Riemann to 0, the components of Riemann to 0, which means you cannot gauge away curvature if it is there. So if there is curvature, it is there. You cannot, just by a suitable choice of coordinate system, make it 0. All right. So here we come. So this is my Riemann. Now as we saw that these gammas are related to the first derivatives of G, and thereby gammas have an interesting property. This gamma and G, if they are compatible, then we saw that the covariant derivative of G must vanish, which makes the gamma, which has 3 indices, symmetric in these lower indices. Alright, so that's an important property, and that is guaranteed if there is this gamma G compatibility, and this G is of course a symmetric tensor. We could have an affine connection without a metric structure. So there can be spaces where you have an affine structure, gammas, but you may not have a metric. But of course, if you have a metric, then you can clearly define differentiation and parallel transport, and you can obviously have gamma. Okay, so that's important. And by writing the components of the Riemann tensor in terms of finally in terms of G, and noting this symmetry property, there are certain interesting symmetry properties of the Riemann itself which are written, which basically reduces the number of independent components. So as you can see, if you look at the first, like interchange of the first and second and the third and fourth, there's an antisymmetry there. And then if you take the 2 at a time and then swapping them, there is actually, so basically R alpha beta gamma delta equals to R gamma delta alpha beta, which is like if you just interchange this, there is symmetry, whereas flipping within this, you have an antisymmetry. So it's a very important property. And very important, of course, is this result, which is again related, which is closely related to the fact that the covariant derivative of the G's are 0, and you can just show by expansion, just by expanding it out and some initial operations. And this is basically what is called the Bianchi identity. So you see there is a cyclic sum of covariant derivatives of the components of Riemann tensor, and this is basically the Bianchi identity. So very crucial is this Bianchi. After Bianchi, who probably showed it. Okay, now other than the Riemann, so this is the tensor of interest, and this contains the entire information about curvature. So if you know all the components of this tensor, we clearly know everything about the curve. And of course, if all the components vanish, for space-time to be called flat, all the components of Riemann has to vanish. And there are certain contractions which are also useful of the Riemann. For example, the Ricci, which contracts the first and the third, and then finally a scalar. So by repeated contractions of the indices, we reduce the rank of the tensor, and finally we have the Ricci scalar and the Ricci tensor. Now, the reason why these are important will be evident right away. So we just use, this is a set of calculations which I thought would be interesting. So we just start with the Bianchi identity on the top, if you can see, and we are contracting the first and the third index. Why we are doing that? Because the first and the third index contracted gives you the Ricci, as we just defined. So to get the Ricci scalar, we are just contracting the Bianchi identity for the first and the third index, and so we get an identity which involves the Ricci tensor now, and then finally, and of course that minus sign that appears is because we have to flip one of the indices, and thereby from this property of antisymmetry, so R alpha beta gamma delta equals to R minus R beta alpha gamma delta. So this antisymmetry property has been used because we always need the first and the third index to be contracted to make it Ricci. So that's why we had to flip it and thereby introduce a minus sign there. And finally, contract even those two indices and try to get the Ricci scalar. So you get the Ricci scalar and finally this equation. So what you have is an interesting identity, and you have a quantity, a second rank symmetric object. Delta mu lambda is of course symmetric, and R mu lambda is symmetric as well, and in its indices, and the covariant derivative of this object is 0. Now we have already encountered one symmetric tensor whose covariant derivative is 0, namely the metric tensor itself. And this is another such tensor whose covariant derivative vanishes. So this could be probably one candidate for something like the energy momentum. Why? Because energy momentum, as we know in special relativity, finally has to be there's this energy momentum for vector which has to be generalized for fluids to the idea of energy momentum tensor. So everybody knows we have been using this T mu nu all the time. So can you tell me what this finally this T mu nu is? What does it mathematically mean? If I give you a fluid, how would you calculate this T mu nu? What do I have to supply to you? I mean, generally, it could be any fluid. It could be any fluid. It could be anything, so any matter field. It could be any matter field, so to say. How would you calculate T mu nu? Is there a general prescription to calculate the energy momentum tensor?
Basically, it's the fluxes of the different energy.
Right, so that is the physics. So we'll go to, there is of course a mathematical way of doing it. For that you need to define the Lagrangian of the corresponding field, and the T mu nu is basically defined, the definition of T mu nu is basically the variation of that Lagrangian with respect to the metric. So if you take the Lagrangian, so if you have some L matter, and this L for some matter field, it will of course depend on the fields themselves, that also will depend on the geometry on which the fields lie. Right? Because finally, for example, if it's a scalar field, it's like del mu phi, something like this, for a scalar field, right? There is a contraction between these indices, which you can write as mu nu, and introduce a g mu nu here. Right? So clearly, I mean, the Lagrangian of matter fields depend on the metric. And formally, this T mu nu is defined as basically the derivative of this, the functional derivative of the Lagrangian with respect to the metric function. All right, but that's of course one thing, but when it comes to fluids, there is of course a physical picture of what this really represents, and as Manish said, I mean, so basically, so T alpha beta, if you take, is basically, I mean, you can do the same thing here. You can calculate the momenta of once you know the Lagrangian density, you can always calculate the momentum density and the energy density and all these things by taking suitable derivatives, right? You know how to find the momentum density, the pi, what we call the pi, for a field theory. So you can always calculate the momentum density and the energy density and all these things. Of course, the zeroth component will be the energy density of the for momentum. And then this T alpha beta is the physical idea behind T alpha beta. It is basically the flux of the alpha-th component of the momentum through a surface of constant x beta. Alright, so let's just take an example, and let's take an example of a fluid as the one which we are using all the time. So what will be T00? T00 will be the flux of the 0th component of momentum. What is the 0th component of momentum? Energy. Flux through the surface of constant x0, which is time. So the surface of constant x0 would be just the volume, right? The 3 volumes. Now it's 4 dimension, right? The surfaces are 3D. So that's why the 00 T00 is the energy per unit volume. So it's energy density. And similarly T0I. What would T0I represent? What is T0I? T0 is 0 corresponds to energy again. But what is it? It's T0 through I, xi being constant, I being the spatial ones. So what does it? So it's flux. It's per unit area, per unit time. It's a flux. So that's why T0I represents energy flux. And similarly, Tij will be, you'll have the same thing. You'll have what will be Tii, T22, T33.
Pressure.
Well, why?
Because it's normal force per.
Yeah, so you have, so it is a normal force per unit area. It's not normal force, it's normal change of momentum per unit time. So that's why it is force. You have momentum per unit time, which is force, per unit area, which is normal to that surface. That's why you get the pressures. No, no, why? This is true for, this is the definition in a coordinate frame, but if you want to go into, so you can always have a coordinate frame where you can put these definitions, right? Yeah, so to define pressure, of course, you have to do that, yeah. But then you can always change your coordinate system, and once you've written it in one coordinate system, you can choose your own preferred, whatever, lap frame. And how would you do that? And that's an important point. So you write this down in this way, and then you can always change your coordinate system, and you give a boost. So once you have written it down in one coordinate system, you can always transform to your lap frame by giving boost, and thereby you get those U alpha, U betas. So this is just rho p p p for a perfect fluid. This form rho p p p if I say T alpha beta is to rho PPP, this is in a certain frame. Obviously, this is in a certain frame where you are basically looking at this pressure and this definite. This is fine, but to define this pressure, you have to go into that frame, to sit on that frame. But thankfully we have relativity. We can always write down the most general form and not bother about the frame by giving it an arbitrary boost by a velocity. And you know how a tensor transforms under a boost. So you can just take this form, and then you just write down the boosted form of this. So T alpha beta prime will be some lambda alpha gamma, lambda beta delta, T gamma delta. So you choose this, and this is iso boost. And so by some manipulation, you can write finally. So this lambda will have your velocities of the boost parameter, and finally you can write it in the standard canonical form U alpha U beta minus G mu. That's a simple exercise, and that's what it means. Now, last time we said that this energy momentum, what does this thing mean? Comma, this is just a simple comma. What equation does it correspond to? So you have the entire conservation law, because see from the definition itself you can see that if you have the derivative of this is 0, it's going to give you the continuity equation. So we just say that for various things, for energy and momentum, right? So depending on the indices, it will be energy conservation equation or the momentum conservation equation contained in the continuity equations. But in curved space-time, if you know, we have to generalize it, and we have to put this instead of the comma by a semicolon, which will take care of the fact that this conservation is no longer true. So in curved space-time, the conservation of energy momentum as we conceive of it in flat space-time is clearly not true because of these the semicolon there with geometric terms depending on gamma. So clearly you would have to think as if the change or the derivative of this quantity will not be zero and it will be basically a creation or annihilation of energy in forms of some geometric factors. So some energy is possibly lost to geometry. Rather, in other sense, we don't know whether there's a globally everything is conserved or not, because you can have a destruction of energy somewhere and it will just manifest as some geometric term, which is the gamma factors. So clearly you have to include, so that is which in other words means in the straightforward way, energy momentum is really not conserved. You can say it is covariantly conserved, as it is normally said, but that is not really what we mean by conservation. Because if something has to be conserved, this is what it would really mean to be conserved. But anyway, so this is what we have and we have to deal with it. And this equation, T alpha beta, the covariant derivative 0, this essentially tells you that you need something in the geometry sector. So now if I say that we are trying to match the geometry sector with the matter sector, it has to be through this T alpha beta, because now this has the entire information about the mass energy distribution of the system. It's a covariantly conserved quantity, and as we just saw, we have a quantity like this, which is also covariantly conserved, and this is purely geometric. So it is reasonable now to relate these two, and that is what Einstein did. So Einstein said that, well, this quantity, which is purely geometric, the conservation is purely geometric, it follows from Bianchi identity. Basically, this statement is, this is just the contracted Bianchi identity. So if you have a contracted Bianchi identity and this is purely geometric, and there's got nothing to do with matter at all. So this has just got to do with the metric connection and the Bianchi identity. Now I'm making an assertion. Of course, that was Einstein's relativity. Einstein said that this quantity, which he describes by now this tensor, now you see there is this, so it is written in this way, the Ricci minus the Ricci scalar, and of course it's covariant derivative being 0 is purely a geometric result, and thereby, okay, one more question. So it says this is conserved, rather it is conserved in this way, probably, this can in some way be written probably as some kind of an energy momentum tensor which is purely geometric in origin. For example, when we started with the matter Lagrangian, which is a function of G, and we varied this respect to G, we got the energy momentum tensor for the matter fields. Now we ask the question whether this quantity, this equation can be obtained by varying something equivalent, some Lagrangian with respect to the metric again, such that you have this equation. So that would correspond, that particular Lagrangian would correspond to a geometric Lagrangian, and corresponding to that, so we want a Lagrangian such that, again, a different Lagrangian, so that the variation of this with respect to G mu nu, this should give you G mu nu semicolon 0 mu equals to 0. So from this quantity you should have G mu nu. So what is that Lagrangian is the question. So can you actually find it? It turns out that, of course you can, like all Lagrangians are basically constructed in a back calculational way, right? Because you have the field equations first. Because field equations are the equations which which has to be there. And the Lagrangian is usually a construct. From the Lagrangian you say that we use the field the Euler-Lagrange equations, but basically the Lagrangian itself is something which we construct by in a back calculation way because we want to get those equations out of it. So what kind of an action, or rather what kind of a Lagrangian would give rise to corresponding geometric analog of an energy momentum tensor, and that is nothing but your, as we all know, it is this so the action is basically root minus gr. The simplest scalar that you can have. Now what would happen if you had some r square and you have some strange contractions? You can think of this action now as a starting point and you do a series of variational calculus by varying the metric. So you have to vary the metric g mu mu and you just go through those steps. But my question is, if I didn't know what my final field equations we expect to be, then we had no reason just to choose r a priori. We could choose r square, that's also a, or we could choose many strange contractions of Riemann as well. You have r, you have g, and you can do many things. So let me just give an example. So you can have an r mu mu and an r mu rho delta. So you can have a r mu mu and r rho delta. That's also a scalar. And you could conceive of many scalars, starting with the Riemann and Ricci and suitably contracting them. And you could in fact also use the g's to construct a scalar. A good criterion for this action, a good candidate for this action would be a scalar, right? You want a scalar here, a scalar density rather. And of course, this root minus g takes care of the invariance of the volume element, so that is different. So this quantity has to be a scalar. And there are many ways of doing it. Why r? Why suddenly choose r? Why would Einstein even choose r? Anybody knows? Why? If you chose r square, you would get a different equation. What's wrong with those? What's wrong with those? See, finally what Einstein did was that Einstein wrote this mattered Lagrangian plus the geometric Lagrangian together, and he said that the variation of this is 0, and he got g alpha beta equals to t alpha beta times some constant. But if he chose some other thing for this, he would get some other equation which would be the different Einstein's equation. Why does it have to be r? Why does g have to be of this form? There is nothing canonical about it at priori. You can clearly see. If you start with something else, you would have some derivatives, derivative theories or something. What is so special about Einstein's gravity? This is called Einstein-Hilbert action. Why do we use this? It's a very important thing because we always say that this is it, but then there are FR gravities. So people can choose this to be some f of r. Generally. That would be an f of r. No, that is, even those can be checked. Certain kinds of restricted class of FR, they are viable. See, the reason is, and that is true for any theory in physics, and you have to finally map your results to known results at some limits. You always have limits of Einstein's theory in your Newtonian physics. In fact, the constant of proportionality that comes in Einstein's equation, which is finally this, of course you can keep a lambda g, because g is always covariantly conserved, so you can always put a constant of integration lambda, which finally turns out to be very important in cosmology. But this k that you see, the proportionality constant, actually has to be fixed. And more importantly, this g alpha beta, as I said, is of a certain form, and that also has to be somehow fixed. The way this is fixed is basically from our knowledge that in the weak limit of the field, which means if the metric is not too violently different from flat space-time, which means the matter is not curving your space-time so violently that it's grossly different from eta. So you have what is called a weak field approximation. So when you have a weak field approximation, we saw, remember we did this last time, but we had this, the coefficient of T as 1 plus 2 phi, where phi is the Newtonian potential. We incorporated the Newtonian potential there. So that solution must come out. You should be having in the weak limit Newton's Newtonian gravity. The Newtonian gravity has to appear as a weak limit, and in fact that is what fixes. So finally in that weak limit, this should finally boil down to your Poisson equation. The left hand side should be a box, a del square of some phi, and the right hand side should be your density. So that fixes cup, this constant k, to 8 pi g by c square. And that g appears, that Newton's constant appears just from matching. Because Einstein would not know how to put this g, capital G on the Newton's constant, right? He's starting from geometry, he's mapping it to matter, but what he has to match in between is Newtonian gravity. That's where g appears, and that also tells why this particular tensor has this form. So higher derivative theories will not give you Newton's laws, Newtonian law of gravity in its weak limit. Alright? So this is the action you start with, r minus 2 lambda, and this whatever matter fields you have, Lm, that will correspond to a T mu nu on the right hand side, and then you basically have Einstein's equation. Vary with this metric, with this action with respect to the metric tensor, and you get Einstein's equation. So the fields, the gravitational fields, are no longer potentials, they are the metric tensor components. And see, now we are varying this action with respect to the field, which is what we do in mechanics as well. So we are varying S with respect to the g mu nu, and you get Einstein's equation.
Sir, in case of Newtonian gravity,
this tensor is identically equals to 0, but there are geometries and there are special situations where people are interested in this torsion. So then people introduce torsion in the gravity theory as well. So there are such models as well. But anyway, so classical gravity or Einstein, so that's why we say Einstein's relativity or Einstein's gravity has this as this Fr equals to R. And basically our cosmology, at least traditional classical cosmology, also starts with this R. So what you basically need to do, and I think this is from where Pershon started, is this equation, and not this one of course. Yeah. And you make a certain ansatz. Now see, this equation is extremely nonlinear, as you can see. It's probably the first nonlinear equation that you encounter in physics. I mean, absolutely, Schrodinger equation, these are all linear, but this is like a terribly nonlinear equation, and of course, I mean, solution to this is only extremely restrictive. I mean, there are very many formal aspects to it, just finding solutions. But anyway, ideally what you need to do is give you the entire T mu nu tensor on the right hand side. You should be able to plug it in and finally solve for G mu nu, which is what people do. So capital G is a function of little g, and T mu nu, if you supply, which is the matter distribution, you should be able to solve for it. It turns out, I mean, if T mu nu is, as our background cosmology the model tells us, supposed to describe homogeneous and isotropic universe, so there this T mu nu can be written in a very simple form. It can be finally written in a very simple form in terms of just a few parameters and an equation of state. You need to, it's a fluid, the cosmological fluid is expanding, maintaining homogeneity and isotropy, which immediately tells that this G mu nu has a certain form. So basically with that ansatz, with that input, this is the equations that you get finally are your Friedmann equations. This is what you start with. So I think that's what I wanted to say. Basically just storytelling. But yeah, so if you know the equation of state and if you know the form of T mu nu for a universe in which your density field is not homogeneous and isotropic, then in principle you could have solved it. But we really don't know. So if you ask the question, what is the energy, the density profile of the universe, we really don't know. And what do we do for that? How do we, so do we sit? Of course we have solved Riemann equations, we can do that, but a real universe does not look like that. So we need to put in that T mu nu. So what do we do? No, but we cannot. We don't know. We live in a certain part of the universe. We don't even know whether rest of the universe looks like that. So what do we do to write down T mu nu? How do we invoke homogeneity? Yeah, but we still cannot exactly write down T mu nu of the universe. We don't. Yeah, so one way of doing it would be to say that, okay, we do it perturbatively. And we believe actually now that the inhomogeneous universe is basically an outcome of a Gaussian random process. This is something which we have to believe in, there's no other way. We believe that the universe was homogeneous and isotropic, and there were some processes which led to formation of inhomogeneities which were of a Gaussian random nature. So you have a density field now, and which is and the density field that we see today is one realization of a random process.
So you mean that the universe was very symmetric before and
no, they at very early epoch, and there were some processes which caused perturbations to be generated, and the process that generated these perturbations were essentially Gaussian random. So it's like somebody throwing a die, coin toss. Yeah, so our universe that we see today is like a coin tossed at some point of time. So this is one realization. So this is very important actually. So if the picture of the universe that we have is, there is a background rho bar, which is the homogeneous part, and I write this thing as rho plus 1 plus delta, which is your rho, and this delta of R, this is a Gaussian random field. What do you mean by a Gaussian random field? It's a field, and it's a random variable as well. Random variable means there is a probability associated with the generation of this as a perturbation. That is how we see it. Now, so of course this is purely statistical. We have one universe right now, we could have some other thing, right? So if we really want to calculate various things, we have to calculate various averages. Since this is a Gaussian process and this is some realization, we can only talk in terms of averages. Average of various statistical properties. For example, we probably might be interested in things like delta R prime. The product of the overdensities at two distinct points. And we need to calculate this average value. Because these are all statistical quantities, they have probabilities. So how do you do it? Simple, you multiply this and you multiply by the corresponding joint probability and integrate, right? That's what you would do. But we don't know. We have only one realization at our disposal. We have only one universe. We don't know what these large number of simulations of the universe would be like. If we did know, we would be able to find this out. We could actually calculate this, right? We would have found the probabilities of our universe given an ensemble of universes, and we would have calculated this ensemble average. This is an ensemble average. But can we actually do this? So here comes to our rescue the idea that universe is pretty large. And we're going to replace this ensemble average by a volume average, assuming that different parts of the universe, so well, if this be the entire universe, and we are looking at a very small part here, then another small part here is going to be possibly, since this is a Gaussian random process that is generating the entire thing, this small patch some far away, this is going to behave, if I calculate the same things over here, is going to behave as if it is like another realization of this. So instead of actually replicating this universe, which we can't, observationally or otherwise, we say that we are looking at a small part of the universe, and there is what is called statistical homogeneity, which means the statistical properties here and the statistical properties here are not different. This is not homogeneous, this is not homogeneous, but statistically they are homogeneous. Which means you can calculate the statistical quantities here and here and here and here, and you can treat them as your realizations and thereby do this averaging, which is now nothing but a volume average. You are calculating this product in a small volume and integrating over the volume. So this is basically ergodicity. We are assuming that this ensemble average can be replaced by a volume average, and we can do this. When would this average value be a good number to talk about? If we had many such little patches to do this average over, right? Then this number would probably convert to a nice average. If we had a huge little patch, we would only find, say, 3 of these. Right? So that would be a problem. That would be a problem. So that would be a problem because we don't have enough number of realizations to do this averaging, and that would manifest itself as some sort of a noise. This is fundamental to cosmology. We shall come to this in my next talk, but this is very, very important. We need large volumes of observation simply because to calculate these various statistical properties, we need many realizations. Okay? So we shall come to this and what are the various properties of functions, these correlation functions like this, that we shall come subsequently and connect them with observations now. And what we really have to observe to get this. But the important thing is that we cannot write the full T mu nu. You have to have this homogeneous and isotropic background, add up little perturbations, solve the linear theory, and then probably go in some sort of a perturbative fashion. With the understanding that these fields are Gaussian random fields and they have some statistical properties. That is what is the entire, that's what we do in cosmology. Okay, so I'll stop here with this and take a 1 minute break, and then actually I go into what I wanted to basically talk about, 21 centimeters. So I'll just stop here. Forbidden transition. So people who are familiar with atomic physics and transitions, people know, have heard this term forbidden. I mean, so what do you mean by a forbidden transition? By selection rules. Great. So there are selection rules which follows from the time-dependent perturbation theory in quantum mechanics, and there are certain. So what is ruled out? Why are certain transitions ruled out? By selection rules. So what is basically ruled out? What does people calculate when people study transitions? So say one energy level to another, there is a transition. The simplest of all, I mean the most generic form of all processes has 2 levels, and you have a transition, right? When is this forbidden? What do you mean by this being forbidden? Okay, what? No, so what does quantum mechanics allow you to calculate for levels? Yeah. Okay, that's the recipe. But yeah, so I heard something. So quantum mechanics, it teaches you how to calculate probability of transitions. Right? Finally, quantum mechanics is all about calculating transitions between states. You have something in between, please. Right? You have the transition amplitude, and the square of that is going to be the probability. And when people talk about forbidden transitions, it's essentially that these probabilities are extremely small. These probabilities are small, and so small that you ever see it. And by saying that you don't see it, what does it mean? Quantum mechanics will never give an answer 0 for a probability. It would be 10 to the power minus 6 or minus 7 probability. What would that mean? It would mean that you have to wait for that many times of doing that experiment to see it happening once, right? That's the definition of probability. You can see it, but when you say talk in terms of probabilities, and it's a very small probability, what it essentially means that probably, at least in the kind of transition that we are interested in, this particular transition, the probability is so small that even if you take the age of the Earth, I mean, the chance of that thing happening even once is ruled out. It's that small, right? So, but age of the Earth or us, is so minuscule in terms of the cosmological scales that it doesn't matter. You just need a very, very, very large number of particles, gas, and even if that number is like very, very, very small when it comes to Earth, if you have a very large volume of cosmological scales, clearly it won't be forbidden when it comes to astrophysical objects or cosmological scales. So by forbidden, of course, this is something which you can never see in your laboratory, and probably the only place you can see such a transition is gas clouds which are of astrophysical size. Okay, so this is the standard famous, the picture. I think everybody uses this from Caltech. Anyway, so but this is very important because what we almost skip most of the time is this band of blue region, starting from which is from the CMBR decoupling era to the present epoch. So let me just go through this epoch in slide. So this is the thermal history of the universe. So as you know, the CMBR decoupled at around redshift of 1000. So what happened when the CMBR decoupled? You have studied this by now, right? No, so the universe cooled down significantly enough for protons and electrons to form neutral hydrogen, and thereby the photon, which was tightly coupled, starts free streaming, right? That is what is this decoupling era. So what forms at that epoch, at the last scattering surface, if we assume that it is an epoch of instantaneous recombination, usually it actually probably took some, instead of instantaneous, it actually took some time, but assuming that it happened at one slice in the cosmic history, what formed after that was neutral hydrogen. And there was a photons which was just free streaming through the neutral hydrogen. So the universe is predominantly neutral hydrogen, and there is of course dark matter, and then there is radiation which is free streaming. So the entire density field, and of course you know CMBR has slight anisotropies. CMBR is largely homogeneous, but there are small anisotropies, which means small inhomogeneities on the CMBR field itself, which amounts to saying that the density field had small little fluctuations at the CMBR epoch, and they are growing as the universe is further cooling down. The CMBR temperature, how is it falling? So if you look at the CMBR temperature, it is just going as, this is like 2.7. So it is just linearly going with redshift, and this, so Z equals to 1000, it's decoupling epoch. So the universe is predominantly filled by neutral hydrogen, all right? And by neutral hydrogen I mean that it is, and we use this symbol H1, and that fills the universe, and absolutely there is nothing interesting going on. Why? Because the photons are free streaming, and the gas is just cooling down, and the universe is expanding. There is nothing really happening. The perturbations delta are all of, they are small, they have not grown enough, so they are still growing. So everything is pretty boring, I would say. What happens is, after a while, and these deltas are of course growing, and after it has grown significantly, they start forming collapsed objects. The moment they start forming collapsed objects, they sort of they have the gas, this neutral hydrogen, they start falling into these halos, and the first star starts forming. Right? And the moment these first luminous stars start forming, and they start burning, they start to radiate. So the universe gets into a new mode. See these little yellow dots? They represent the formation of the first luminous objects after collapse has taken place. And then there is radiation which is being injected back into the medium. Right? So, some sort of a feedback. Yeah. So what happens is that these energetic photons now, from these new sources that have formed, they now start ionizing the medium around itself. Because there is neutral hydrogen background, which was completely neutral till they started to get reionized. Now this is reionization by virtue of these photons. But these photons are not the same mere photons, but photons coming from this collapse, from these luminous sources that form. So this process starts, and as time goes on, clearly more of these deltas starts collapsing, and there is a large number of such objects, and even the radiation that goes out from these sources, they form these bubble-like structures, and this bubble is like essentially ionized from inside, and these bubbles, these ionized bubbles, they coalesce with one another, and finally the entire universe is pretty much ionized. So the universe was an ionized plasma before the epoch of decoupling, namely before CMB are decoupled. That was because of the sheer heat that was there in the universe. The universe has cooled significantly down in its evolution, but again at a much later epoch, and this process of the formation of the first luminous object is what starts the epoch of reionization. And well, there are debates, and it's actually one of the most important areas of research as to tell when did this thing start. When did reionization start, and when did it end? So we now believe that approximately at redshift 20, these first luminous objects started forming. That is roughly correct. And this was over by redshift 6. So by redshift 6, everything was ionized. So we presently live in a universe which is ionized, completely ionized. Now don't think about your own planet. We don't occur in this scheme. The kind of scales you are talking about is galaxies a point. You can imagine. So at redshift 20, these first luminous objects started forming, and the universe got reionized by redshift 6. So 20, redshift 6. These are some numbers. Ionization. So there was this epoch between redshift 1000 and 20 when the universe was largely neutral hydrogen and nothing else. There was nothing, traces of helium was there which formed from nucleosynthesis and some higher metals, but the universe was largely filled with neutral hydrogen. So to observe the universe during this entire epoch of its evolution, we have to basically look at this neutral hydrogen because there was nothing else. The CMBR photons are free streaming. If we could map out this neutral hydrogen density as it evolves through from redshift 1000 to the present epoch, we should be able to tell everything, we should be able to map out the universe and its evolution all the way. The CMBR map that you see, what does it really represent? The map, see, look at the CMBR map. What is it really, what is it an image of? So it is basically the image of the last scattering surface, because the photons that you are detecting in your WMAP or whatsoever, in your CMBR experiment, they are basically coming all the way from the last scattering surface, right? So that is the image that we are seeing. These photons are essentially they're unabated. Their journey is essentially free. There are some minor anisotropies forming along the journey, but largely they are coming free streaming, and thereby it is just the map of the last scattering surface. So we really don't know how to image the universe. So that has a lot of information, right? The CMBR anisotropic image. But we really don't know how to image this universe between that redshift of 1000 to redshift 0, which is present. So that is, and the only way to do that would be to somehow trace this neutral hydrogen, because that is all that is there. After redshift 6, most of the universe, as I said, is ionized. These galaxies and stars have formed, and the universe pretty much looks like as we see it today. There is a lot of these galaxies and stars have formed, quasars have formed, and the collapsed structures are out there. The universe is extremely inhomogeneous. So CMBR, which was very homogeneous, what was order of homogeneity? 10 to the power minus 5. So 1 part in 10 to the power 5, that was the degree of homogeneity. Here the inhomogeneity leads to almost order unity, more than order unity. So this delta becomes order unity. Thereby you have these collapsed structures, right? So the gas, which is largely neutral, is now completely ionized and only occurs in very, very, very small regions in neutral clouds. So redshift 0 to 6, between these epochs, the neutral gas is very small, of course, and it occurs in what are called extremely dense regions of space and in very small clouds. How come they survive this ionization? It's because they are so dense in these regions that they shield themselves. So that by a process called self-shielding, so these gas clouds, they remain self-shielded from the ionizing radiation field around, and they form these small clumpy objects at redshifts below 6. So that is what we see now. Neutral hydrogen clouds in little small bundles, in little clumps. And these clumps are usually called damped Lyman alpha clouds, for a reason which we shall come to. So this is basically the thermal history that we know, and this is also the history of the neutral gas as it cools down. Alright, so clearly, as you can see, you cannot see the universe other than through photons. We still don't have gravitational wave detectors. We really don't have a neutrino map. We can't see neutrinos either. So the only way to see the universe is through photons. So we need luminous objects. So we can see the last scattering surface through the photons that travel to us from there. So we can see the local universe from galaxies, because galaxies emit light. So we can know where the galaxies are. You can have a map of the galaxy distribution, which people can do. But galaxies and stars, as we saw, they only formed at a much, much later epoch in history. So it's only in the recent times that these things formed. So if you really want to probe the universe into its large evolution history, its entire period of time from redshift 1000 to say 20, there was no structure as such. So the only thing that was there was neutral hydrogen, so you cannot see that part by using galaxies or quasars or anything. However, this neutral hydrogen medium acts like there are clouds of this neutral gas, and what it does is that it modifies the CMBR photon, or it does things to the CMBR photon as it passes through it. And possibly, if we could detect that, then we could probably have a hold as to how, and understand what is going on during the passage of light through the medium. So we have to understand the entire physics of photons which are traveling through a neutral hydrogen cloud. So this is, say, a CMBR photon, and this is the present we are looking at, and there is a neutral hydrogen cloud sitting over here, and This neutral hydrogen, as this photon passes, emits and absorbs radiation as the photon passes, and thereby increases or decreases the temperature of the CMBR.
What redshift is this one?
It's all over the place. It's all the way from 200 to redshift 1000 to the present. In the present epoch, of course, there is no neutral hydrogen, it's ionized hydrogen. Neutral hydrogen are in small clumps, but for a large part of the history, the entire universe is full of this gas of homogeneous
We
density.
are not currently concerned with exactly when this was. It's just
Yeah.
like that.
Yeah, so let's assume that this cloud is located somewhere, and we are interested in what it could possibly do to the CMBR photon, which we could detect, right? And here comes this transition that I was talking about, namely the 21 centimeter transition. So what is this transition? It is basically a hyperfine transition between the two states of the ground state of the hydrogen, where the electron spin and the proton spin, they are parallel or anti-parallel. It's a spin-spin coupling, thereby it goes into the hyperfine, very weak, and the transition, as is shown, is in a rest frame. So if the gas is at rest, this transition is at this frequency of 1420 megahertz. 1420 megahertz. Or in wavelength unit, it's 21 centimeters. This 21 centimeters is the rest wavelength of this transition. Alright? So what can happen is that a CMBR photon, as it passes through, might get absorbed, right? Or there might be emission of this. There can be added photons coming due to emission, and thereby over here there can be either a dip in the temperature or an increase in the temperature, depending on what kind of transition is taking place in this gas, right? So what would dictate that? What would dictate whether you see the CMBR against this cloud as a dip or as an emission? So that would depend clearly on the processes going here, right? And that process, which is, if I say that the transition that I'm talking about is 21 centimeters, and there are n1 number of such particles, and n1 number of H1 atoms which are in the higher of these two states, and they're anti-parallel. So this is 21 centimeter, and let's say there are n1 atoms here and n0 atoms here, then the equilibrium between these two states would be governed by a temperature which is called the spin temperature. So as you can see, n1 by n0 is g1 by g0, which is the degeneracies of the two levels. One is a triplet state, one is a singlet state, and T star is just the energy corresponds to frequency of 1420 megahertz, is h times that. And then it's the Ts which dictates which population would be higher. Would it be N1 or N0? So we are defining a temperature for a gas to be equilibrated between these two levels. See, that is what we do in statistical mechanics. So we have these two levels, and there are populations in these two levels, and we are defining a temperature which we now call the spin temperature, which controls the populations at these two levels. Right? So depending on, if N1 is very high, that would correspond to a certain spin temperature. What would that be? So if you can pump more and more atoms over here, the spin temperature will clearly rise. So the spin temperature depends on the relative population between these two levels. Alright? So I'll just, yeah. One more thing is that this particular radiation, this 21 centimeter that is emitted, say, from a cloud, of course, as like any other radiation, will get redshifted. Right? We know the universe is expanding as this photon is coming. So when you actually measure it on Earth in telescopes, that photon will have a wavelength which is larger. Or in other words, the frequency would be smaller. So 1420 megahertz would be some 1420 by 1 plus z. When you actually detect it, right? So if you can tune your telescope frequency to some value, say 200 megahertz, and you're receiving photons, right? If that frequency is so tuned that 1420 by 1 plus z is that value, then essentially you are looking at that particular redshift. Is this clear? So 1420 megahertz is my rest frequency, and 1 plus z is a factor by which it's reduced. So this is some mu observed. So by tuning my observation frequency, by looking at some observation frequency, I can basically look at different redshifts from which the gas is coming, from which the radiation is coming. This is very important. So by considering a gas at some redshift z, the emitted photons will basically get reduced by this factor, and you would observe it at some frequency. So by tuning the frequency of your telescope, you can basically continuously look at different slices, right? Because you know the rest frequency. If you're interested in that particular line and the effect of that particular line, since this is a line transition, it has one specific frequency, and thereby, just by tuning your telescope to different frequencies, you can image different redshifts.
But sir, you told us result of ultrafiltration, so how can you detect exactly what's going on there?
Right. So we have the CMBR photons coming. We have the CMBR photons coming. What this 21 centimeter does is that it either changes it as a dip, or it takes away some photons from the CMBR by absorption, or it adds some photons to the CMBR in form of an emission, and thereby you see this as an emission or an absorption depending on where the gas is. So the feature that you finally observe is either an emission or an absorption against the CMBR background.
So it is not better to look for some other conditions which are allowed and which you can observe.
No, that will saturate it. So we need something very weak, because otherwise that transition will saturate and you won't be able to see it. It will be completely locked up, it will be whitewashed. So we need a weak transition, because we don't want that particular frequency, that particular light to get saturated completely by the gas. Because it has to traverse all the way, and if it is completely saturated, it won't you won't see it.
You want to look for some weird sun.
We are interested in this transition because of its weakness, because of the fact that it is so weak. So this equation, if you look, the top one basically says that this is essentially in the radio. If you look at the frequency and the wavelength, it essentially falls in the radio part of the spectrum. So when you have a frequency which is in the radio part of the spectrum, you can completely approximate your Planckian spectrum, Planckian law, by Rayleigh-Jeans approximation, right? And you can write the intensity clearly just as this 2kT nu square. That's just the approximation of the complete Planck formula in the Rayleigh-Jeans limit. The simplicity that we have over here is that instead of that I being represented by a complex Planck function, it is just denoted as clearly a linear function in terms of T. So you can associate a temperature with the intensity in this approximation. So I is basically some T, and of course multiplied by frequency square. So you have this temperature which is associated with the intensity. And that is only true because this is in the radio regime and everything is in the low frequency regime. Now, as I said, this intensity as it goes through this medium changes because of the gas presence, and it is given by this equation minus alpha I nu plus J mu. So J mu, what is that? That is like some kind of a source. It's adding something to the intensity, and alpha I nu is an absorption which is taking away some bit of the intensity, right? So which is basically called the radiative transfer equation, and it essentially tells how this intensity of a photon changes as you go through a medium, right? So if you associate with absorption, emission, and of course the CMBR photon temperatures by the formula given on the top, because all these are in the radio, and then you measure the difference of the temperature as this light goes through the gas. So here you would have intensity I some S, and here you would have IS plus delta S, where delta S is this. And basically you can take the difference of this and write it in terms of the temperature. Because both these I's are basically temperatures. The only way this emission takes place, alright, this source function J mu is clearly going to be related to the spin temperature. Because that is what is causing this transition to take place. So Ts is related to this J mu, which is the source, and alpha is of course something which has been taken away. So finally you have the difference that you have between this and this given in just in terms of the temperature. And this tau is a quantity which is of crucial importance, and we shall be coming to it again and again. Tau is just this alpha ds integral. So alpha is at absorption, and the integrated effect of the absorption coefficient is basically what is called tau. It's optical delta. So you can just to do that, basically you have to. So if I write down this equation, I nu ds equals to minus alpha I nu plus j nu. This is for a given frequency, and then I divide this whole thing by alpha. So I have alpha ds equals to d tau. So I have d I nu d tau equals to minus I nu plus j nu by alpha nu. This quantity is called a source function, and then you integrate it. When you integrate it, you get this, assuming that I nu is basically related to T, and S nu is related to Ts. And you get this. So finally what happens is that the change in the temperature of the CMBR photon as it passes through the gas with some spin temperature. So this spin temperature is related to this J nu by alpha nu, which we are assuming to be constant for a small region of the gas. And so you have this dip in this temperature delta Tb, which is proportional to the spin temperature and the background temperature. The spin temperature is the property of the transition that is taking place in the cloud, the 21 centimeter transition, which is either adding or taking away photons. So in this case, it's an emission. So photons are emitted in the cloud. So of course, that is behaving like a source. And then there is an alpha ds, which is absorption of the CMBR photon as it passes through the gas. So both of these processes are taking place. So there is an absorption of CMBR photons as it passes through the gas, which is accounted for in this term minus I nu, and this is the source term, which is the emission of 21 centimeter photons. So finally this is an equilibrium, and what it amounts to is a change of the temperature, which is given by delta T, and this is at the and this is at the redshift, which is the local frame, at the local at that local region of the gas, and then we just scale it by 1 plus z to tell what it is going to be now.
What is T star?
T star is the 1420 megahertz times h. It's h nu by kt. H nu by kb. That is T star. 1420 is a transition frequency. It's the energy difference corresponding to the two levels, h nu by kt. So we are just defining that Ts as setting up the equilibrium between the two population levels. How much time do we have? So now, this tau, which is alpha ds integrated over the path, tells us how much photon is being absorbed, right? Because that is what it means. Alpha ds related to the absorption. This absorption is related, again, if I say, to the cross section, right? Because any absorption process is basically finally related to the cross section of the process, which is relating to the absorption. So finally, if you know the atomic physics, you can calculate this alpha from experimental data. That is absorption coefficient. That will clearly depend on the gas. All right. So what it turns out, and is this tau, which is, I write down this tau again, which is integral alpha ds. What this depends on. Now, if you write down the formula for tau, which we shall do in the next time, in the next class, this, of course, and you can intuitively immediately tell that the amount of absorption that is taking place is going to be crucially dependent on the density of the gas. If there is a density of gas which is very high, then of course there is going to be more absorption. So absorption or amount of photons lost, which is related to tau, is clearly dependent on the gas density. So this tau is clearly proportional, as you can see, to this number in H. I put a proportionality sign because there are lots of other things, but what is important is to see that it depends on the difference between Ts and Tr, and it also depends on the gas density. So the dip in the CMBR photon temperature as it goes through a gas cloud, neutral gas cloud, is proportional to the density of the gas, because that will dictate absorption, and is also related crucially to the spin temperature of the gas, which tells the population levels of the two kinds of species, the triplet state or the singlet state. So this Ts dictates the equilibrium of the two levels. This is purely related to the density of the gas. Now I'll just discuss this figure, and it's a very important information. Now see, look at the purple curve T gamma. This is basically the temperature plotted against redshift. So T gamma, as you know, is just a linear function of z, right? It's T0 times 1 plus z. So it just goes linearly. There are two other temperatures being plotted. One is the gas temperature, which is just the kinetic temperature of the hydrogen gas. And then there is the S, which is the spin temperature of the gas. T gamma is the CMBR photon temperature. Now, of course, at very high redshift beyond 200, 300, 400, near the decoupling era, of course, there is collision between the remnant electrons. So see, there are some remnant electrons which have survived recombination. So they are still there. And there is collision process which keeps the gas temperature, the photon temperature, and the spin temperature. The spin temperature and the gas temperature are kept at the same level through collisional process between the gas itself. So gas atoms, they are colliding with each other and keeping that spin temperature at an equilibrium state. The CMBR temperature is maintained at the gas temperature because of the presence of these remnant electrons, which is still maintaining the equilibrium. Right? So all the three temperatures are same till a point, say 200, after which the gas temperature starts falling off at how would the gas temperature go? Gas temperature will just go as 1 plus z squared. 1 plus z squared, because that's how the gas density falls. So the gas Tg, 1 plus z whole square. Adiabatic expansion of the gas, it just cools off like that. So the temperature of the gas, because of adiabatic expansion, this falls off as 1 plus z squared. The CMBR still goes as 1 plus z in photons. The spin temperature remains coupled to the gas temperature for a while because of collisions. Because the spin temperature is basically related to the transitions of the gases. So the equilibrium between these two is maintained by collision process between the upper state and the lower state. What starts happening, and that is And you can see that the spin temperature actually is below the CMBR temperature in the regime between 25 and 200. This is the epoch, these are the times when the spin temperature is lower than the CMBR temperature, and thereby you would see the difference as an absorption, because T gamma minus T spin, that is going to be positive. So the spin temperature is actually lower than the CMBR temperature, so you see the 21 centimeters in absorption, so it's lower than the CMBR temperature. What happens at low redshifts is that you have formation of structures. So at low redshifts around 25, structures start forming and you have photons which inject energy into the system. What happens is there is a sudden change in the population of the triplet state. And one such mechanism is what is called Lyman alpha pumping. So you have these two states, and this is your 21 centimeter. What happens is, at low redshifts, there are photons which excite these levels to some higher states. Usually this is, say, the Lyman alpha, n equals to, so in its ground state, n equals to 1. N equals to 1 to n equals to 2. And when this is what is called Lyman alpha pumping. So this is the first Lyman series, from the first orbit. When it decays, it doesn't go here, it goes here. So what it does is that through this level, the population in the higher triplet state keeps increasing, N2 keeps increasing, thereby the spin temperature keeps increasing. So at low redshifts, there is a pumping which is basically Lyman alpha and even X-ray induced pumping. What does is that the spin temperature is growing, and you see the spin temperature grows up exponentially. So at low redshifts, you will see the 21 centimeters as a temperature which is higher than the CMBR, and thereby emission. In this entire epoch between 200 and 25, you will see this in absorption. Prior to 200, the CMBR temperature and the spin temperature are the same, and thereby you won't be able to see 21 because you won't distinguish it from the CMBR. You will see that it's the same CMBR. You can only detect the 21 centimeter signal only if it manifests itself as a little emission feature or an absorption feature against the background CMBR. CMBR is there. So you can only probably detect it in some direction of the sky, provided there is an emission or an absorption. And that can happen only for redshifts less than 200, all the way to 0, of course. But the good thing is that, so you cannot see the universe between 1000 and 200 by any means. You cannot see it, even using the hydrogen, but at least this transition you cannot see it. What would be the frequency at which you have to tune your telescope to see redshift 200? It would be 1420 by 201. Extremely low frequencies. It is very tough to observe things at those low frequencies. Redshift of 1 would correspond to, or redshift of 2 would correspond to some 350, 400 megahertz, which is roughly what our telescopes function at, those frequencies. But in this entire regime, from 200 to 0, what is this frequency? Let's take it 200. And 7 megahertz. Absolutely difficult. And redshift 0 would be 1420 megahertz. So from 7 megahertz to 1.4 gigahertz, you can continuously change the frequency of your radio telescope and thereby image the universe slice by slice from all the way from 0 to that epoch. So that's why we say that 21 centimeters, unlike CMBR, gives a tomographic image. It's a 3D image. You not only have the information on the plane, but you have a 3D imaging through the change of frequency. CMBR gives just one sky, just one surface. But here you can keep tuning the frequency of your observation and thereby go to the next and the next and the next Z slice and get a 3D map of the universe. So that is of huge importance. So I will end today's talk with the classification of this entire region of evolution into 3 parts. Dark ages, as I said, dark ages is this entire region between 1000 and 20, where, 20 because that's when there was no structure forming and there were no luminous sources, the universe was dark. And epoch of reionization is when around redshift 20, first luminous structures started forming and the universe started to get reionized. By redshift 6, the process of reionization was believed to be complete, and what we have now is a post-reionization epoch where neutral gas is contained in small clumps of self-shielded gas clouds. And the entire dark ages cannot be seen using 21 centimeters, all the way from 1000 to 20, but we can explore a large part of the dark ages all the way from redshift 200 to 20, because before 200 all the 3 temperatures are at the same level, we cannot see it. So 200 to 20 we can see the universe as a tomographic image using 21 centimeter in absorption. So the dark ages are seen as absorption features in the redshifted 21 centimeters. We always say redshifted 21 centimeters because 21 centimeters is in the rest frame. And epoch of reionization and the post-reionization epoch, these are going to be seen as emission features. So when we are looking at the universe today, the local universe, redshift 1, 2, 3, 4, 5, 6, and explore the reionization process. So those would be seen in emission. So 21 centimeters in emission. So, so we'll continue next time with how to do cosmology using this gas.